Hello. So we're going to deal with an example of a circuit that uses resistors in series. Now the diagram is already given to us here with the corresponding values of the resistors in ohms and uh, the potential difference, or the EMF, supplied by the battery. But later on we're going to move this from ideal battery to what happens if there's some internal resistance in it. So resistors in series aren't that bad, but we're going to find out certain things about the individual components and about the entire circuit in general. Okay, so let's see what we're given. I am just going to be a little bit lazy, if that's okay. Is that okay? Okay, I'm going to imagine that you all said yes. And use the circuit as our given. Okay, and our goals are somewhat different. First, we find the equivalent resistance for all of them, and resistors in series aren't that bad. And the current in the circuit, and that which just happens to be the total current as well, because it's just in series. And also, let me put C down here. Calculate for the potential difference at point A right here. Now I'm going to imagine that it's from point A to a point here, the potential difference across essentially across that part of the circuit. And D is given the EMF of the battery, find out the internal resistance. You can put small r or r int. R int is, I think, is fine. Okay. Formulas that we'll need. I actually have the formulas for the resistors in series right above here. As you can see, it's just pretty straightforward. Okay. I just realized there's something wrong with that slide. Okay, so this is what should apply here, and these should apply there. So for the resistors in series, let me reiterate that. The resistance, equivalent resistance, is just simply R1, in this case R2 up to R4, and the current total is actually the same current going through I1, I2, I3, and I4, so you don't even have to label it at all. It's not even a total current, it's just I, really. Okay, but the potential differences, that is what is the sum of its parts. So the potential difference supplied by the battery is equal to delta V1 plus delta V2, delta V3 plus delta V4. And of course you'll also need Ohm's law that actually relates all of these quantities together. Okay, so I'm just going to go ahead and in the solution just borrow this formula right here, if that's okay. And just add all the resistances together. This is for part A. So I have 2, and I'm going to do a shortcut. And you can do this on your own solutions too, especially if you have an instructor that's really picky on units. So the units are on the outside, and just add all of those together to get, let's write it here in the end, 18 ohms. Boom. And that's it. That is our answer for A. Okay, now what is the total current? Now the total current, you'll need Ohm's law for that. Okay, so delta V equals I times R. I was getting ahead of myself. So we're looking for the total current, so divide sides by R. Okay, and you're going to get and now the delta V will be the voltage applied by the battery right there, and this R is actually the R equivalent. So we're going to get 6 volts from the battery and 18 ohms, and that will give us current. I'm looking at the solution in front of me, so I know the answer is pretty much 1/3 of an amp, which is equivalent to about 330 milliamps. That's about considerable, as a matter of fact. Okay, and that is our answer for B. Getting things done. Now for the potential drop across point A, take note here we're actually already moving through the first resistor, which is 2 ohms. And now you already know that the current, capital I, is 0.33 amperes. So we can easily calculate for the potential drop using Ohm's law again. This is R1, I believe, and so that just becomes 0.33. Now you notice how the answers all kind of build up in each other, especially in problems like these. Oops, times 2 ohms. Okay, and that will just give you, take note, even though we're multiplying amperes times ohms, we should get an answer that represents what the units for potential in volts. Okay, so the potential drop is not that big. So part of that means part of the 6 volts is being used up. Just 2/3 of that is used up in the first resistor. So as you can see, and just as a side note, the resistances actually increase. So the potential drop gets bigger and bigger and bigger. Okay, but all of that should add up to what? Should add up to 6 volts. Okay, it has to go somewhere. You just can't add or create electric potential energy out of nothing. Okay, the law of conservation of energy still applies. Okay, and the last but not the least, we're given if the EMF of the battery is given to be 6.2 volts, what is the internal resistance? Now I'm going to borrow a formula for internal resistance, which I should have earlier, is the same current IR, R for R internal. Okay, and so pretty much it's just plug and chug. 6.2 volts minus 0.33, and R int, and the voltage of the battery initially is 6 volts, so we have to solve for R int. So I'm going to move this to the other side. Okay. No, actually, pardon. I'm going to move this to the other side and move that to the right side. And so after this shuffle, it's going to look like 0.33 R int. I don't have to put that int. 6.2 minus 6.0 volts, and then all I have to do is divide both sides by 0.33. Those are actually amps. Okay, cancel that, and I get 0.2. That's 6.2 minus 6 volts divided by 0.33 amps, and still give me units of ohms based on Ohm's law. Okay, especially since I'm trying to find a resistance here. Okay, and the answer that we get is 0.6 ohms, which is good. That means the internal resistance of that particular battery is not that much. Okay, now what they usually do is they put a really big load resistor in front of it so that it essentially becomes negligible. Okay, so that's our example of resistors in series. Take note of what is the same for all of them and what is being added together. Okay, hope you all understood that. You can rewind and play back and pause as you wish, and hope you all get to learn something and enjoy. Ciao.